Welcome back. Last lecture, we looked at symplectic manifolds, introduced their definition, looked at the morphisms between them. I didn't really present anything in the way of examples there, well, apart from a really simple example. And the objective of today's lecture is to give you a huge source of examples of symplectic manifold. And these examples will form the foundation for many of the calculations we'll do in the rest of this course. By studying these examples, understanding them more deeply, we will see properties that we can generalize and see in other symplectic manifolds. So not all manifolds are symplectic manifolds of the type I'm about to describe today. Indeed, we already heard last lecture of a symplectic manifold that won't be of this type, namely the sphere. But a great many are, and in particular for physics, the examples that we're going to cover today will be the standard physics examples of classical mechanics. So the first, I can tell you what the example is already. The example is the cotangent bundle. So this turns out to be a symplectic manifold, but well, that needs a little bit of justification. So that little bit of justification is what we're going to do today. So let me remind you, or I didn't actually define it in this course, although it's kind of, I hope, clear once you've seen the tangent bundle, what the cotangent bundle might be, but let's just remind you. So let X be an n-dimensional manifold Okay, let it be an m-dimensional manifold, and well, T star X be its cotangent bundle. Now the thing that we want to emphasize throughout this lecture, and probably most of this course, is that just like for the tangent bundle, the cotangent bundle is also a manifold in its own right. So we'll give this a name, we'll call this M. So if you remember, the tangent bundle to a manifold is a manifold itself, also is the cotangent bundle. And we'll be a bit more explicit. I'll introduce some coordinate charts on this cotangent bundle. And then we'll also get onto the topic of looking at differential forms on M. And that's where things can get a bit mind-blowing. So let's define some coordinate charts. Namely, we'll write them as T star calligraphic U. And what are they? Well, U is a coordinate chart on our original manifold X, and this T star U coordinate chart is given by a list of two n numbers, two n coordinates, x1 through to xn, psi1 through to psi n, where these are the coordinates that come from expanding any one form in this basis here. I'll write that on the next board. where. So we let that be a chart of our original manifold X, and these xi's are defined by writing an arbitrary one form at the point X as a linear combination of the basis one form dx1 through to dxn. So that's how we build our coordinate charts on this manifold. We take original coordinate charts and we augment them by adding in the coordinates of an arbitrary one form. Easy peasy. Now, does this get to be called a manifold? Well, not yet, because we haven't shown that the transition functions are smooth. So are the transition functions smooth? Or for that matter, even well defined? Let's take a look. So let X be in the intersection between two coordinate charts of our original manifold X. And we're going to try and express a point in one chart in terms of a point in the other chart. The coordinates of a point in one chart in terms of the coordinates of the same point in another chart. And then we hope that what we get as the transition function between these two representations is smooth. Better be, right? So there you go. Got some charts of our original manifold X. And then we got some one form in one. A one form in one chart. See what this looks like in other bases, other chart. So the pair x psi is a point in T star x, which is equivalent to M, which we're trying to prove is a manifold. So because we've got this basis expansion for this one form, what we want to do is understand what are its coordinates in terms of the other coordinate chart here, these x primes. And we know how to do that, right? We know how to express a one form in a different coordinate basis. You just have to take dxj and express it in terms of dxk prime. Right? So but that, of course, defines our new psi k primes, the coordinates in the new coordinate chart, and we're well on our way to proving that these transition functions are smooth. In fact, we've basically done it with this line. So these things here, these are smooth. And of course, xk as a function of xj is also smooth. So we found a smooth way to map a point in the original coordinates x psi to a point in the new coordinates xk prime psi k prime. It's all good. There. Good. I consider that basically enough justification at this level that the cotangent bundle is a well-behaved manifold. You've got to show that these charts cover the cotangent bundle. Oh, that's a nice little exercise. Now we have a wonderful way to produce many, many examples of symplectic manifolds. So procedure works as follows. When you learn the definition of a symplectic manifold, it's not clear that there even are symplectic manifolds beyond the trivial flat one, R2n. In particular, it's not even clear that there's kind of non-trivial ones. We see the two-sphere, that's the first example we have of a non-trivial symplectic manifold. Maybe that's a sporadic example, maybe maybe the definition of symplectic manifold is so strict that there is only, in fact, R2n as an example. Well, that's obviously not the case, but we still have the task of coming up with a nice supply of good examples that aren't trivial. Now, you can't just insert manifold and check if it's symplectic. That's a hard job. It requires that you find a 2 form that's closed. That's not necessarily trivial for any given manifold. But one thing you could do is find a procedure that, say, given a manifold, uses it to produce a symplectic manifold. Maybe it's a different one, but somehow related to the original one. And that's exactly this procedure here. So the way we're going to construct our symplectic manifolds is we have it has as input any manifold, like that's a big class of examples, right? And then we form their cotangent bundle, and we'll see that the cotangent bundle has a kind of canonical symplectic structure. Canonical means standard, right? There could be other symplectic structures. And that'll give us a huge source of examples. Now, to relate this to physics, like how would you have discovered this as a physicist, as a construction? Well, think of X as the configuration space of a particle. Just the positions, right? So X, you think of X as you think of a particle moving on the manifold X. Now, classical dynamics tells us that that doesn't completely specify the state of the system, right? If you only know the position of a particle, well, that's not much use to you because that particle might be having a different velocity or in particular, a different momentum, and therefore be executing a different trajectory. To fully specify the state of a particle on a manifold, constrained to live in some manifold, you need a momentum, you need additional data. So we'll call this the physicist. So you consider a particle constrained to move in a manifold X. Now there's plenty of examples where this can happen. You could imagine that a particle is moving freely in three-dimensional space or n-dimensional space, if you like. And there's some restoring force that pushes this particle onto a submanifold, very strong force. And it turns out, I don't think I did this at the beginning of the course, that you can think of this as an embedded manifold. Right? The submanifold that the particle is allowed to move on is an embedded manifold when this restoring force is infinite. So, you know, some examples might be you have a particle moving in three-dimensional space that's bound into moving in a sphere by some restoring force that pushes it onto a sphere. Maybe there's a magnet or something that holds it onto the sphere. So to fully specify the state of the particle, a state means that you can predict its future motion given the data of the state. So the position of the particle is just the coordinates of the particle on the manifold. But also its momentum, which is a list of other numbers. And as we'll see later, you can identify momentum with a 1 form in the cotangent bundle, or a 1 form at the position x. Yeah, I know this is really badly. This is the coordinates of a 1 form P. There we go. So once once you've got the coordinates of a point and its momentum, then you can always predict its future motion. So there's some Hamiltonian in the background. So this data, what is it? Well, we have a name in physics for specifying the data of a bunch of positions and a bunch of momenta. It's called phase space. So phase space is a higher dimensional manifold associated with a lower dimensional manifold. If you have a particle on a line, phase space is two-dimensional, not one-dimensional. It's got exactly double the number of dimensions. So that's kind of interesting because, and furthermore, phase space has this property that, you know, if you know a point in phase space, then you know the future trajectory of that point. So the state there is fully, a state is a point in this phase space and fully specifies all the future motions after you solve the equations of motion. This construction that we've defined abstractly here is none other than phase space for a manifold, or a particle moving on a manifold X. Now, we've got to give this thing some symplectic structure. We haven't done so yet, and we're not even going to see how symplectic structure has got anything to do with Hamiltonian flows until maybe a couple of lectures away from now. But it turns out there is a canonical one. And I'm going to introduce that now. Phase space has a canonical symplectic structure.
Another question?
Yep.
Why we are able to identify the momentum of a particle when it's over the one form of the...
Well, we can identify, so the question is, why can we identify the momentum of a particle with a one form? I can give two answers to this, right? One is, you know, you can, right? Because you just write down the components and can interpret it as a one form. Another is you can think of the velocity as a tangent vector, right? Yeah, you can think of the velocity as a tangent vector, and momentum, what does it do? Well, it eats a velocity vector to give you a number. So I hope that's sort of some justification. The momentum, if you write down, yeah, I think it's linear. Perhaps a better answer for why a momentum is a cotangent vector is just think of how it transforms under a change of basis. Maybe that I should have said that first. All right, tautological and canonical forms. So I've given you an argument from physics that somehow this cotangent bundle is like phase space, and that this is going to be our example of a symplectic manifold, but I haven't yet given you a closed two form, right? I haven't given you a symplectic structure on this thing. That's what we're going to do now. I'm going to do it twice. And there's a great potential for confusion in this part, in this definition, because we're going to have forms and forms on forms. So we'll proceed carefully. So here's the coordinate version of the definition. So if I say nothing, just now we're going to define a two form on M. So the whole way to deal with this next part of the lecture is to selectively remember and forget that T star X is a manifold with some structure. So we know that Tx star x is a manifold. Okay, fine, no problems. So if you forget that T star x is a manifold, it's just a manifold. So two forms are two forms. But it turns out that it's going to be very useful to remember that M has this structure here of a cotangent bundle, and we're going to interpret some points also as one forms. You'll see how this works in a second. So we're going to define a two-form on M, well, on the chart in particular. There it is. I just defined for you a two-form on a chart. As written, it's more or less obvious that this is coordinate independent as a definition. But it does need some justification. And that justification comes from how does this thing look like in another coordinate chart. One has to be a little bit careful with things like this, right? This is the coordinates of a one form. So how does this look in another chart? I mean, could go wrong. Well, I'll argue now that this definition is independent of the coordinate chart you took and therefore is well defined. Okay, so let's argue why this thing is coordinate independent. So consider a one form. On T star U, which is a subset of the manifold M. And consider which one? Well, consider this one. Alpha equals thing has a name, it's called the tautological form. It's called the canonical form. Now here is the moment where there's great potential for confusion. This is a one form on M. I'll write that out. Alpha is a one form on M, on a manifold. It's also a point in the cotangent. It's also a one form in the cotangent bundle T star X. That's not controversial. Now, note, if I do d alpha, then I get minus omega. So well, I've got to do d psi dx, and then wedge with dx, but that's 0. And then we're going to do d psi j k, and we wedge it with d psi k, and we get a minus over a minus sign there. But alpha is intrinsically defined. We can express it into terms of another basis, and we see that we get the same answer. If you change basis, change coordinate chart, then the rules for the transformation here exactly match the rules for the transformation there. So we're done. So version 1 of the definition. Now, when something is coordinate independent, you often want to see it defined in a coordinate-free way. It's a bit silly to introduce coordinates and then argue that those coordinates don't matter. You'd rather see the object defined in a way where you have not introduced coordinates throughout the whole definition. So we're going to come to a second definition of this two-form, which doesn't involve coordinates. And also something not entirely desirable about this definition is we do it with respect to one chart. We'd like to see this thing defined globally. Here's how it's going to work. So we have M, the manifold M. And M is T star of X. Get rid of the bracket. Now there's a canonical map from M to X. How do I draw it? Do I draw it above or beside? Above. And this map is called pi. It's called the projection map. What it does is it throws away the information about the one form part of the coordinates of M, and it just gives you X. I'll define it in here. So pi of X psi is just X. That's how pi is defined. Pi is a map from M to X. And what we're going to do is look at the pullback of this projection. This is coordinate free. Pi is just this projection to the underlying manifold. And now let's look at T star of X. And we're going to look at the pullback of this map here to T star of M. Now here's the point where you could, the potentially confusing point is that that is equal to T star of X, right? So there's a great potential for confusion when you look at the cotangent bundle of a manifold, which itself is a cotangent bundle. Yep.
Why is it the D there? Isn't that what the star does? if pi is mapped from M to X, then pi star is a map? No.
Pi star is a map from
yes.
X to M.
But
So
yeah,
D
okay.
pi star is a map from T star X to T star M.
Okay. Maybe this.
So X is D is a map from X to T star X, right?
Yes. Oh, yes. Yeah.
So let P be a point in this manifold M, forgetting that it's a cotangent bundle. It has coordinates, just if you recall, x comma xi, and xi be the element of the cotangent bundle of X at X defined by these coordinates. So we're going to variously interpret this as a one form and also just as specifying a point in M. And the difficulty in this definition is defining this tautological one for alpha. So once you've got alpha is in defined coordinate-free way, then you get omega for free, right? You just apply a d to it and it's all good. And we're going to do so by defining alpha p is d pi p, the pullback of this projection applied to psi, that one form psi at the point P. And this is an element of, well, it's a one form on the manifold M at the point P. Oops, not P, but pi of P. So That's it, that's already the definition done. Equivalently, you can define alpha p by how it acts on a tangent vector on M, point-wise. So let V be a tangent vector on M at the point P. But what's that? Remember that a tangent vector on M is a tangent vector on the cotangent. Bundle. And we're going to see, how does alpha p act on V? Well, it eats the vector and gives you a number. So, but what number does it give you? Well, let's look at the definition up here. And we see that it gives you psi, which is now defined in, is a one form on X. What does it eat? Well, it eats T pi of P, d pi P of V. Psi has to eat a vector on X. How do we get that vector on X? We push forward the vector on M down to X. Now we have a vector on X, and we eat it with psi. And remember, and where does the psi come from? Well, the point P itself is of the form x psi. So the data here is specified by the point where you're defining this number. I'll draw a picture in terms of an example.
Excuse me?
Yeah.
Before you raise it. I'm still struggling, I think, with this d pi. So is it, it's not d after pi star, right? It's d pi, okay. Then for me, because sometimes this notation is altered, because normally d is x on
Functions.
yes, that map to R. And if not so, then d is star, like pullback, right? So then we
The pullback of a map
yes.
written is usually written with d, name of map, star. And that's a linear map from the cotangent space to the cotangent space. So this is distinct, different from d as the exterior derivative.
Yes. So, but how would you evaluate d pi p of vp? You would
d pi p of
push
vp.
vp forward, right?
Yeah, vp is pushed forward here. So if we look at the right hand side
here. Of pi.
Yes.
Okay. So, and this is the pullback of the pullback of pi.
Yeah.
Okay.
Pullback of the push forward of pi.
Of the push forward.
And d is a push forward.
D is a push forward. So d pi is a push forward, right?
D is the push forward.
Yes. No, d pi is the push forward of pi. So
Push forward? No.
Pi is push forward from the tangent bundle of n
okay, let's
bundle of x.
I knew this was coming. I knew this was coming. So my mental stack is very short, and when I put too many items on the mental stack, it falls off the bottom. So I'm going to write down some symbols to all these words that we've been saying so that we don't have to keep them in my mental stack. So if you have a manifold M, forget all this. Forget. You have a map, let's call it pi, just happens to call it pi, to another manifold X. Then the push forward traditionally written d pi is a linear map from the tangent space on M at a point P to the tangent space on a point pi of P in the target manifold X. And then the pullback, just for completeness, traditionally denoted d pi with a superscript star. Yeah. Sometimes I think early in the lecture I put a subscript star.
Yes.
I guess I'd prefer not to do that in future because I see a great potential for confusion if I mix up the subs and well, whatever. Either way, right? I've just defined it there, so that's fine. That's a map going backwards from Tx.
I think that first step was misleading.
Okay.
Thank you.
Awesome. And that's how this is all well defined. Yeah, an example, right? I was going to draw something down like an example. So let's just take the real line as our example. I know I said we'd restrict to compact manifolds, but well, you can cope. So this is the trivialista, well, arguably the slightly less trivial example of a one-dimensional manifold. And the cotangent bundle to R, sort of canonically, you can identify it with just R cross R. And that's our manifold M. And then we have some coordinates. X, P on R2. And then pi is the map that forgets the momentum. Just tells you the position of the particle. And then let's define this tautological form. And we should get PDX. We should, if I haven't made a mistake. Where's the XDP? What have I done? PDX, right? We can check that. Yeah. Oh, I see. Yeah, that's slightly unfortunate notation over here. So I've used P for the point. Yeah, okay. I will actually change this notation then, because that there's always that's unnecessary to use this, the same notation for different things so close together. So there we go. That's what I claim is the the tautological one form. And then we have alpha on x, y, a tangent vector on M is specified by two numbers, Vx, Vy, and that is equal to psi d pi p of Vp, which is just Vx and that is, I believe, y. Yeah. Okay, so here's the manifold M. It's just two-dimensional space. Here's the manifold X. This is the x-axis, the y-axis. The projection pi, takes a point x, y down to the x-axis. Just gives you the x-coordinate of this point xy here. Now, a tangent vector on M is specified by two numbers. And when you apply a projection and you take the push forward, you just forget that second coordinate. I didn't write out omega. Omega is minus d alpha, which is d of y dx, which is minus that. And the other example is hardly different from the first.
Question.
Yeah.
What's the psi in this example?
Psi is y.
Okay.
Right.
Sorry, but I don't think it's right.
I don't think it's right either. Should be y vx. Thanks. So the second example, also not very complicated, is the cotangent bundle associated to the circle S1. And what is that? That's just a cylinder. I'm actually I think I'll end up only drawing a picture rather than writing anything out, because it's the same thing. So here we have fibers of this projection map pi. Pi goes from M to X. And if you have a point on this manifold, x theta, say, theta y, theta being the coordinate on the circle, then that gets mapped to just theta. It just throws away the momentum information. This point here on the cylinder tells you what is the momentum of this particle on the circle. And what else is there to say? The canonical tautological one form should be y d theta. I'll leave that as an exercise, right? And the canonical 2 form, omega is d theta wedge dy. Now that is a function of 2 tangent vectors on this cylinder. Just want you to bear that in mind in the future. This cylinder here, we're trying to make this cylinder into a symplectic manifold, and we do so via the fact that it projects down to this one-dimensional manifold, and that you can separately interpret it as a cotangent bundle. I'll leave it to you and to the exercises to explore more complicated examples. For example, you might be interested when X is the 2 sphere, then you find that the cotangent bundle is a 4-dimensional manifold in its own right. It's the Cartesian product at any point of R2 with R2, so it's locally a 4-dimensional manifold. So the phase space, another way of saying that is the phase space for a particle on a sphere is 4-dimensional. You need the 2 position coordinates on the sphere, and you need the 2 momentum coordinates to tell you what is the momentum of the particle. Okay, now let's argue that this tautological form is quite natural. At the moment, it's pretty arbitrary, right? I just cooked up this recipe, it works. Let's argue that it has a notion of naturality associated with it. And the way it works is we're going to see, is this definition consistent with diffeomorphisms between manifolds? So if you have 2 manifolds, x1 and x2 be n-dimensional manifolds, with their corresponding cotangent bundles, and suppose that these 2 manifolds are diffeomorphic. So they're the same. So under the notion where 2 manifolds are deemed to be equivalent if they're diffeomorphic, these are the same manifold. Then I want to argue that there's a natural map between the tautological one forms on these 2 cotangent bundles. So that if you worked out the tautological one form for x2 and for x1, then you'll see that they're compatible with each other under this notion of equivalence, so they're equivalent. So you don't end up in this perverse situation where you might write down a tautological one form for this manifold and one for that manifold, and even though they happen to be diffeomorphic, and then you find somehow these tautological one forms don't match with each other. They don't behave well under diffeomorphism. I'll argue that that's not the case. They behave very nicely under diffeomorphisms. Which extend or lift F. So just because there's a diffeomorphism between x1 and x2 doesn't mean there's any kind of diffeomorphism between Tx1 and T star x2, T star x1. But there is. There's a natural diffeomorphism between t star x1 and t star x2 called f hash. I think it goes the other way. No, that's correct. M1 and M2, yeah. What makes it natural? Well, if you restrict to its action on x1 and x2, then it gives you back f. That's the idea of a lift. So this is M1 here. This is M2. So if you've got some point in M1, you do the map on it and you project, then you should get the same thing. Not enough space. So we'll just define the map. So let x1, xi1 be a point in M1, and we're going to define the map f sharp, f hash. To be the point P2. It's the point P1. So what is P2? Well, it's a pair x2, xi2, where, well, we know what we want xi2 to, x2 to be. Should just be f applied to x1. That's definitely an element of x2. And what do we want xi2 to be? Well, we're going to define it via pull back of this map f. So xi2 is whatever it takes so that when you pull it back you get xi1. So this is natural. It lifts f because if you just apply the projection pi on both sides, you just get back f. And you've got pretty much only one option for how you're going to map a one form in one manifold to another, namely by the pullback. So it's compatible with that as well. So that's sort of like the thing you would not naturally write down. But what I haven't shown, and what's your exercise? you've got to prove that this is a diffeomorphism. All right, just got to prove that that map is smooth, and furthermore, invertible and has a smooth inverse. So whenever you have a nice map between two manifolds, you have a nice map between their cotangent bundles. A natural map, it's one you would write down. Now the last step is to argue that the tautological one form on this manifold M2 pulls back to the tautological one form on M1 via F sharp, or F hash. And if so, then you'd be should be fairly happy that that's a natural definition of a one form, or that our definition of the tautological one form obeys the right kind of manifold-free invariance. And to do that, we're going to need a proposition so we're going to lift a diffeomorphism F sharp So we're going to look at this pointwise. How does this F sharp map pull back one forms pointwise? And this is, let's call this equation star. No. We'll call this equation star. So pointwise, what this is saying is that dF sharp star P1 on alpha 2 pulls back to at point alpha 2 at P2 pulls back to something at P1, namely alpha 1 at P1. That's what pullback means. Yeah.
Did you forget the push forward of F sharp, or did I use some notation in the first?
Did I forget the push forward of F sharp?
Because you write D, F star, is F sharp there, but not there.
Yeah, okay. That's a notation thing. So
Okay.
yeah, we're in this kind of awkward world of hundreds of years of differential geometry notations, and some of them get mixed. And when you use multiple sources like I do, then some authors put the D in here, some don't, and so it's going to happen. I have to keep your eyes peeled. Oh yeah. Pulls back. Sorry, I said push forward, didn't I? Sorry about that. Pull back. Okay. Here's some facts to help us with this argument. Firstly, by definition of F sharp, P2 is F sharp P1, right? Easy. But that happens if and only if P2 is of the form x2 psi2, where that's f of x1 and df star psi2 equals psi1. First useful fact, it's just the definition, indeed, of the F sharp map. And then we use the definition of our tautological one form. So if you evaluate alpha 1 at the point P1, then that's the push forward under the projection map pi 1 of psi 1. Okay, now let's look at this diagram. There we go. Definition of F sharp, definition of tautological one form. Now let's look at this diagram here. So we're going to walk around this diagram in two ways and see if we get the same answer both ways. That's what commutes means. So if you're a point in M1 and you apply the projection map, then you've got a point in this configuration space X1. And then if you do a diffeomorphism, you end up with a point in X2. But if you instead did F sharp on this point up here, well then you've got the point x2, comma, psi2. And then you project, well you throw away that psi2. But x2 is just equal to fx1. So it's the same thing. Yeah.
Isn't it clear at that point, having a bundle map between these bundles, that any coordinate-free definition matches because the bundles are?
Isn't it clear, is the question, because they're coordinate-free definitions and we have a bundle map? Yeah.
Okay.
Actually, I'm not completely convinced it's clear. So we have a coordinate-free definition of something here and a coordinate-free definition of something here. And we have a map that we've defined specifically here.
Yeah, maybe it's the wrong bundle for what we defined, right? That might be a problem.
And so it's not clear that this map respects the coordinate-free definition here. So this map is specifically chosen, right? We invented this map.
Yes.
But there could be multiple inequivalent maps between M1 and M2. And furthermore, these inequivalent maps might do nasty things to our coordinate-free definition here and here.
Oh, okay.
So we want to show that this particular map that we've chosen out of thin air, because we believe it's natural, is compatible with this thing that we chose out of thin air that we believe is natural. And if we had chosen some other smooth map between these two spaces, might not have been the case. So I think there's hard work to do here. And in fact, you know, the actual proof is a couple of lines. I mean, maybe if you phrase it in terms of fiber bundles, which I haven't done myself, it might be an example of it might be a trivial result because you've set the definitions up when you do your fiber bundle theory so that it is. But then you'd have to introduce fiber bundle theory, and I'm not quite willing to do that at this point. So. All right, let's just compute left-hand sides and right-hand sides and hope all is well. That's the left-hand side. Now we insert the definition of this tautological one form. Probably the only complicated step is the chain rule, which we're going to do now. Right, you have df times d pi, well, it's the same as d of pi times f sharp. But now we know something really great, right? We know that if we do f sharp then pi 2, that's the same as pi 1 then f. I think that's correct. Oops, other way around, right? And then we use the chain rule again. Projection of P1. So in summary, we write out the left side, and then we write out the definition of alpha 2. We see that we can apply the chain rule to the pull back. And then we see that pi 2 of f sharp, or f sharp of first f sharp, then pi 2. Very frustrating that compositional notation is the reverse of arrow notation. Is the same as f of pi 1 by that diagram there. And then we unapply we do apply the chain rule pullback. We get to this expression here, and then we just recognize, oh, that's what we had over here. And then we recognize this thing indeed as the tautological one form on M1. And so it is that the tautological one form definition is compatible with this notion of naturalness between two cotangent bundles. All right, and so we learn as a corollary that this df star is a symplectomorphism, so that's a corollary. Or F sharp, if you like. Sorry, I should have written F sharp. It is indeed. That's far less crazy. Because it pulls back the 2 form on M1, on M2 to M1. All right, I think we'll stop here today. In the next lecture, we'll start looking at Hamiltonian dynamics and try and relate Hamiltonian dynamics to all this symplectic manifold stuff. It'll take a good number of lectures. We'll have to go into Lie derivatives, which we haven't covered yet, and a bunch of other good stuff like that. Okay, but for now, thank you very much.